Welcome to the lecture on section 3.2 in pre-calculus. Last time we started to look at logarithms and natural logarithms, so we will continue that process today as we are going to look at some various properties associated with these. So let's go ahead and dig right on in. So one of the first things that we learn with these is how to go from this logarithmic form to exponential form. So here is our first problem. Let's say that we've got log base 9 of 1 over 81 equals -2. So in this logarithmic formula, I don't really know what that means, but it's a three-step process. If you take your base of your logarithm and raise it to this power, it is set back equal to the number on the left. So 1, 2, 3. You're not ever going to be playing any tricks with us with these problems. It's simply, can you apply the 1, 2, 3 thing? Can you take the base of the logarithm, raise it to the power of the number on the right-hand side, and set it back equal to the number on the left-hand side? So let's keep practicing this. Let's say we've got log of base 32 of 4 equals 2/5. If we're going to write this exponentially, we take the base of a logarithm, we raise it to the power over on the right-hand side, and it's set back equal to the number on the left. Again, you can use your calculator. You can double check the arithmetic, but 32 to the 2/5 power is indeed 4. So since we have learned to go from this logarithmic form to this format that makes more sense to us because we know how to do exponents, we're going to reverse that process. So they're going to give it to us in exponential form, and we're going to rewrite it back in logarithmic form. So let's say that we had 9 to the 3/2 power equals 27. You want to write that back as a logarithm. So I'm going to write log, and I'm going to skip myself a significant amount of space, and then that equals 2 sign so I can kind of fill in as we go. So the base of the exponent right here is the base of the logarithm. The exponent goes over on the right, and then what it's equal to goes back over to the left. So the log base 9 of 27 is equal to 3/2. Is how we go from that exponential format of 9 to the 3/2 equals 27 to that logarithmic form. Let's do another one. Let's say we had 24 to the 0 power equals 1. That is in that exponential form. We know anything to the 0 power is 1. We want to write it back in logarithmic form. So I'm writing log, I'm going to skip myself a significant amount of space, and then we're going to fill in the gaps. The base of our exponent is 24. That is the base of our logarithm. The power of that 24 is 0, so it goes to the right, and it's equal to 1, so that number goes back to the left. Hopefully those 4 problems there allowed you the opportunity to understand how to transition from log form to exponential form or vice versa. The next concept that we're going to go through is how to evaluate a logarithm. So let's say that we had log base 25 of x, and we're going to let x be equal to 5. One of the properties of a logarithm is if the base of the logarithm and the next number are the same, all 3 of those are going to cancel out, and your exponent is going to be your answer. So when I take this problem and I plug in the 5 for x, knowing that I would need to use that property, I know that I'm going to have to trial and error a lot of powers of 25 rather, to get a 5. So these might be problems that come to you very quickly, and sometimes these are problems you're going to spend a lot of time going, okay, what can I try next? So thinking about some powers of 25, I know 25 to the first is 25. I'm trying to get a 5, so I don't think that's going to work out if I go any higher. And in fact, if you wanted to just try it, just for peace of mind, 25 squared is 625. So I know I need to be going down in my power. So if I go to 25 to the 0 power, that gives me a 1. I'm trying to get a 5. So 1's too much and 0's too little. So let me see if I meet in the middle. 25 to the 1/2 power. So that would be a square root, or if you're going to do the 1/2 power, make sure you put a set of parentheses around it in the calculator. And bingo. So I am taking that 5 and I am replacing it with the 25 to the 1/2 power. That's really the key to the whole problem, is how can you unlock that? Because the next part of the problem, if the base of the logarithm and the next number are the same, all three of those pieces cancel out and is your exponent that you're left with, that's your answer. So our answer to this problem is 1/2. This right here, going through these powers, is the hardest part of the problem. Let's try another one. Let's say that we have got the log of x when x equals 10. Now, in that previous question I worked, I clearly had a base of 25. I do not see that subscripted number with this problem. So if it's not seeing a base, then it is by default 10, because we know our number system works off a base of 10. So this is very easy. Log base 10 of 10 is going to cancel out. Whatever this power is right here is our answer. And our power is an imaginary 1. All right, let's do another one. So let's say our equation is log base b of x, and we're going to let x be the square root of b. Remember that anytime you have a square root, its exponent is a 1/2. Imaginary 1 here making the numerator, imaginary 2 here making the denominator of that fraction. So once I get to that phase, again, log base b of b is gone, and that exponent you're left with is your answer. Right, I'm going to look at some other ones that cancel too. Let's say that we had 5 raised to a power of log base 5 of 3. So it's very awkward here, but if the base of your exponent there and the base of the logarithm and the exponent are the same, they are also going to cancel out, and it's just going to leave you with that quantity in the exponent. So that is a very awkward cancellation, but it does cancel in that direction as well. All right, another thing that we would need to work on is working with solving different types of equations. So let's say that we had log base 2 of x minus 3 equals log base 2 of 9. So notice with this problem that we have got log base 2 on each side of the equation, so we can cancel that out. And we would just need to continue solving the equation that's left. So if we wanted to get x by itself, we would need to add 3 to both sides, and we're done. Our answer to this equation would be 12. Let's look at another one. Let's say that we had log of x squared plus 6x is equal to the log of 27. Again, when you see a log that does not have a visible base written there, know it's 10. And just like the previous problem, the logs are going to cancel out from each side. So we need to continue to solve that remaining equation that is left. So since it is a quadratic equation, I am going to move the 27 over to the other side. And I now need to turn my attention to factoring. When it comes to 27, I've got 1 times 27 and I got 3 times 9. I'm looking for something that would add or subtract to a positive 6. So the minus 3 and the plus 9 is how we can make all of that happen. And as we set these baby equations equal to 0 and solve, those are the two solutions. Now, it's always a good habit to check your equations because, again, we could have that situation we've done everything right and then it just doesn't check out. So if we do 3 squared plus 6 times 3 equals log 27, let's see if that works out. That would be 9, that would be 18 rather. That first solution works. Let's see if this negative 9 one works. So that would be 81. That would be 54. That's negative. 81 minus 54 gives us 27. So that works as well. One thing that you do need to really consider is you cannot take the log of a negative quantity. Your calculator will yell back at you that it's not able to compute that. So at any rate, just know checking is very worthwhile because you may have some solutions that do not work out. So I want to switch gears now, and I want to start working with that E. We saw the E when we were doing our continuous compounding formula. So we're going to continue to practice this concept with the natural logarithm as well. So just by default, ln is a natural logarithm. What it's called. Formula-wise, ln is equal to log base E. So we're really going to go back through everything that we've done previously with the log. Now we're going to use the E and the ln instead. So let's say we had the natural log of 7 is equal to 1.945-ish, and we want to use that 3-step process. So we would want to go ahead and write ln as log base E. And it's much easier. We're going to take the E, we're going to raise it to the 1.45-ish power, and that's going to be equal to 7. That's applying that 1, 2, 3 thing. Base of the logarithm to the number on the right for power sets back equal to the number on the left. All right, let's say we had natural log of 1 equals 0. Remember, natural log is nothing but a fancy way for saying log base E. So now that we have the 3 things, here goes, e to the 0 power equals 1. 1, 2, 3. And let's also reverse that process. So if we were given that exponential form, can we go back to that logarithmic form or that natural logarithmic form? So we would write log, skip ourselves some space. The base is the base of the logarithm. The exponent goes over on the right, and the plain number goes back over on the left. I wouldn't totally be having a conniption if you left it like this, but log base E, the best way to write that would be natural log. All right, let's say that we had e to the 2x equal to 3. So we're going to write log, we're going to skip ourselves right much room, and then we're going to fill in. The base is the base of the logarithm, the 2x goes on the right, and the 3 is back on the left. Log base e, we can write that a little bit cleaner. It's natural log of 3 for the left side. No need to solve, we're just practicing, can we write it exponentially or not? All right, let's practice using the natural log button on our calculator. So let's say that we had an equation f of x equals 3 natural log of x, and we're going to let x be 0.74. So obviously we need to plug in that number for x. Now if you've got the Walmart calculator, log is here and natural log is right below it. So in your calculator, 3, and then click your LN button, 0.74. And let's round this to 3 decimal places because we're probably going to get some funky numbers. Negative 0.90 and keep it a 3. Let's try a new equation. If our equation was negative natural log of x and we let x be equal to 1/2, there it is, plugging it in. Now I need to turn the calculator. So negative sign, ln, 1 divided by 2. 0.639 rather, and then keep a 3. Right, let's go through and see how the base and the next number cancel out. Let's say we had the problem, the natural log of 1 over e squared. I'm going to use these properties to simplify the expression. I know that ln is just a fancy way for saying log base e. Now if I can get the base of the logarithm and the next number to be the same, they're just going to cancel each other out. So I know using my exponent rules that I can take an exponent down in the bottom, bring it back to the top, and it would just make it a negative. So 1 over e squared is the same thing as e to the negative second. And that's what unlocked this problem for those 3 things to cancel out. Our final solution would be negative 2. Let me give you another one. Let's say we had the natural log of e over pi. So I know in the top, ln is just log base e. So when those things cancel out, whatever this exponent is here is all I'm going to be left with, and that's an imaginary 1. So 1 over pi is a fantastic answer. If you wanted to bring that up to the top, we can say that that's pi to the negative first. Either one of those is fine. And that really crazy simplification one, let's say we have e raised to the natural log of 1 divided by e. I'm going to go ahead and replace that natural log as log base e. So if this and this are the same, then they cancel out this way. And then whatever you're actually taking the log or natural log of is your answer. So 1 over e is how that would simplify that. Now, when we were working with logarithms earlier, we also solved equations with them. So let's solve an equation. Let's say we've got the natural log of x minus 7 is equal to the natural log of 7. So on both sides of the equation, we have ln, so they're going to cancel out. And we just need to continue to solve this equation. So we would be adding 7 to both sides. And 14 is the answer for x. That's the only value of x that would make the equation true. do another one. Again, taking the log of both sides, toodaloo to that. If we can solve this equation, we'll have our solution. So I'm going to subtract 23 from both sides. And I see I've got a difference of squares. So either we can factor that, or let me go ahead and move that 25 back over and take the square root of both sides. Remember, when you take the square root, make sure to include that plus or minus. So we have two solutions here. We have a positive 5 and we also have a negative 5. So we talked about earlier, it's really important to check these to make sure your solutions are right. So let me plug in that first one. 25 minus 2 is indeed 23, so that one's good. And then when I plug in a negative 5, that one works too. So two solutions to that equation, a positive 5 and a negative 5. So I do want to go back and look at the domain and some asymptotes when it comes to these graphs. We'll do the log and the natural log of these. So let's go back to this equation. Let's say we have g of x is equal to log base 6 of x. So when we are looking at the graphs of these, when we think about what we're taking the log of, we would be taking whatever that quantity is and setting it greater than 0. Now that asymptote is whatever we're taking the log of equaling 0. So there was no equation for us to solve here. So in this particular problem, I can only do values that are greater than 0 when I type that in the calculator. And at 0, I have this guiding line. We see that swoop in the graph following that asymptote, never touching it or crossing over it. Let's go with log base 4 of x minus 3. So the domain, whatever we're taking the log of, gets, I set greater than 0. And then the asymptote gets set equal to 0. So we are going to have to do some solving here. We need to add the 3 on both of those. So at x equals 3, I've got a guiding line, and I can only take the log of values larger than 3. So like 3.0001, I could actually do the log of 3. You would yell back at me. Let's also do that for the natural log. Let's say that we had the natural log of x plus 5. Again, the concepts are the same. Asymptotes are greater, or domain rather, greater than 0. Asymptotes are equal to 0. So we're looking at anything larger than negative 5 will work, but at negative 5, we've got that guiding line. Now there's really one that you have to be very conscientious of, and that's one where we have a negative x. So let's say our equation was the natural log of 3 minus x. The domain starts off the same, and so does the asymptote start off the same. But we've got to spend a little bit more time with the domain. I want that x to be over on the left-hand side, so I'm going to move the 3. And then anytime you have a negative quantity inside or in front of your x, you've got to take the opposite of each term. So the opposite of negative x is positive x, the opposite of greater than is less than, and the opposite of -3 would now be a +3. So any value smaller than 3, I could actually type in the calculator and get an answer, but at 3 is where I've got that guiding line. So real quick, want to show you the graphs of these. So if you wanted to look at the log of x, that's what the log of x does. We have this guiding line over here dropping down on that y-axis, and then it curves over. If you want it to look at the graph of the natural log of x, the natural log of x is the one in blue. So again, we've got this curve here going on, but it continues over in the first quadrant and goes a little bit higher than what the log does. But as you put more numbers into the equation, we can make those shifts up, down, left, right, reflections upon the axes. We can stretch it, we can shrink it, we can have lots of fun, but these are what the two basic ones look like. So again, nothing over in the second or the third quadrant because we cannot take the log or natural log of any negative quantities. That's why we have this asymptote at the 0. So hopefully you got a little bit of information today about how to write log and natural log problems exponentially and reverse that process, how to type them into your calculator, how if the base of the logarithm and the next number are the same, they cancel each other out, and then also what the domain and the asymptotes are for your equation. So at this point, you can go ahead into WebAssign and complete your work. And I will see you next time in section 3.3 where we look at the properties of logarithms. See you then.